Right. Okay. So let's summarize what we call the concepts of you know of you know of heating and cooling. Having watched an hour of me show you some demos in the lab, let's talk about let's summarize what they showed us and the key ideas. So there is one starting principle at play with things why things get hotter and colder, and that's because thermal stores of energy will move from hot areas to cold areas. Hot things, things that are hotter than their surroundings, will cool down. Things that are cold in their surroundings, like ice or whatever, will warm up. And that's because of a fundamental law of physics called the second law of thermodynamics. Thermal energy will always move from a hot object to a cold object. If you want to do the opposite, if you want to move things the wrong way and you want to build something like a fridge freezer, you got to put energy in. But so as long as we just avoid putting energy in, what we will have is this idea is that thermal energy will naturally move from hot things, which means is a high temperature, to cold ones, so cold things, so low temperature. And that's a natural law, okay? You never get a cup of tea that's sat on the side, that's left there for several days. It won't suddenly reach boiling point of its own accord. It won't, because there is, it's at the same temperature as the surroundings. Okay, and there are three ways in which this can happen: conduction, convection, and radiation. Okay, so there are three methods of heating. Okay, so let's take them in turn. So conduction is first one. Conduction is how thermal energy is transferred through a solid. And what happens, it's always in solids. All solids transfer thermal energy via conduction, but some are better than others. So something like a metal, we call that a good conductor. If something's bad at it, like rubber, plastic, we call it a poor conductor, or more commonly you might call it an insulator. And the way that happens is if you've got one area of the solid which is in contact with a source of thermal energy, so something at a high temperature, then it will warm up through the solid, the whole thing. And if you sort of I wouldn't advise you do this. I wouldn't advise you stick a metal pin in a flame, because eventually you'll burn your hand. It's very, very silly. Why does that happen? Well, it's because the particles have kinetic energy. That means they vibrate a little bit. And the more that we heat them, the more they vibrate. And they will therefore bounce into their neighbors, making their neighbors warm up. And eventually what you'll do is you'll spread that heat through the vibrations of particles. So that's all we need to know. So conduction occurs in solids and is where energy is transferred from hotter particles via vibrations. Okay, now different solids, good or bad this, metals are very good conductors. And non-metals are poor conductors. Okay, sometimes we'll use the term insulators as sort of the opposite. So, that's all that happens with conduction. So we can look at that. That's the principle of play. Particles will vibrate, they'll bash into the invisible guns, which will then spread those vibrations around and around. And eventually what will happen, if you keep heating it up, you'll end up with all the particles vibrating at the same rate, with the same amount of kinetic energy, which means that that whole thing has reached what we call a thermal equilibrium at that point. They're all at the same temperature. But that is heat transfer through solids. Convection. Convection. Might need more space for this one. So convection is how energy is transferred through liquids or gases, or to be more precise, fluids. Okay, so fluid is a term that's used for either of these things. A fluid, because in these things, the particles can move over each other. So like, if we tried to heat this up and this was a liquid, then this particle might just go over there somewhere, and it doesn't need to necessarily, it's not fixed in a certain position. So in liquids and gases, particles are free to move, which means we set up convection currents. Now, how does that occur? Well, it occurs by the fact that when you heat up particles, they gain kinetic energy, and they therefore will take up more space, and that makes that area of the fluid less dense. And if it's less dense, it'll go up. And what happens is, something's got to come in to replace it, or will come in to replace it. It's colder stuff. Okay, and so you set up a cycle of convection. And this is the thing to remember, is that essentially, if you're warming up a room, your radiator mostly works via convection. What happens is particles, every time they do a whole cycle, by the time they've gone round to it, they will be slightly warmer than when they first started. And so every successive cycle, they're getting warmer and warmer and warmer, which is what, is the thing that heats up the room. So, convection occurs in liquids and gases through cycles called convection. Currents. Okay, so that's the thing. And I'm going to actually, I'm going to do a slightly briefer here. We want a bit more space. I'm just going to talk about, there is a sort of series of steps, that we want to talk about. Like, how do we set up this cycle? So we'll have it in this set. So the particles, not that, that's spelled that wrong. So the particles are heated, they gain kinetic energy. Now that therefore means that they got kinetic energy, the particles spread out. Okay, because they're now spreading out, they're taking up a larger space, same amount of particles, but they're now over in a large space. Now this means, and I caught myself actually when I watched through, I was a bit poor in my choice of language here. This means that I'm going to pretend this is happening in a gas. Okay, the gas, not the particles, the gas becomes less dense, which means therefore it rises, which means and then it is replaced by colder, denser gas. And eventually, the gas cools and sinks. Because as it travels round, it will transfer energy via some collisions with the ceiling and with other air particles and then with the window. So this is how we set up a convection current. So this is the sort of the how to get, if you see a sort of 4 or 5 mark question, here's when you talk about with a convection current steps. That's the kind of key important thing. You can feel convection. You don't just need a hot thing. Don't just need a hot thing sort of at the ground level. You could also have a cold thing that's a bit more elevated. If you want a very quick experience of that, open your fridge door with no socks on, and you will feel that colder, denser air which falls out of the fridge. It'll fall down, and it will make your feet cold. So you can always do that as a little experiment. Let's put that back over there. So that's kind of what you need to know for convection. Hooray! All over the place. This is the thing that drives all the weather patterns all over the planet. Now, next thing. Radiation. Because it is that infrared radiation. And this is what's emitted by any hot object. So hot objects are emitting radiation all the time. cold objects that will be absorbing it. So radiation is sort of like, it's all around you. You just can't see it all the time. So radiation is absorbed by cold objects and emitted by hot ones. Radiation is a wave and can travel through a vacuum. Now, sometimes you might realize, hang on, we've used the word radiation before. We used it when we talk about nuclear radiation. And it's somewhat annoying. They're using the same word to describe two things. Like radiation from a nuclear isotope is different from, a gamma ray is just that's similar to infrared radiation, but alpha and beta particles are not the same. And so you might go, oh no, how do I know which one to use? What am I talking about here? Well, if they see something like a Leslie's cube, if there's colours involved and it's to do with something cooling down, that's thermal radiation. If it is something to do with the atomic nucleus, then that's nuclear radiation. So strictly, you could put the word thermal above it in front of it. But it's often very clear what it is the situation that you're looking at. If you're in a nuclear power station, probably going to be more likely to be nuclear radiation. If you're looking at a kettle, very few kettles are powered by atomic energy. So, or at least within the home, you could argue they come from a nuclear power station. But the key is just to think about what it is talking about. So radiation, we talk about that. We often talk about thermal radiation or infrared radiation. It's a wave, it's an electromagnetic wave, which means it's transverse, can travel through a vacuum, moves at the speed of light, so on and so forth. It's affected by colour. So colour can affect how good or poor things are at absorbing or emitting radiation. And the idea is, as we can see from the Leslie's cube, is that dark colours are really good at giving off radiation. Light colours, not very good at all. And so that is some of the experiments that you saw. Light colours also happen to be very poor absorbers of radiation. Dark colours tend to be very good absorbers of radiation. So dark colours tend to lead to faster changes in temperature. Now, and that leads to complications for infrared cameras because when it sees less radiation from the white side opposed to the black side, it thinks they're at different temperatures because that's what it's trying to calibrate. They're not. They're at the same temperature because it's hot water of the same boat. But that's the thing that confuses it. So, so the color as an object affects how well it emits and absorbs radiation. Dark colors are good. Absorbers and emitters. And then we've got light colors. Are poor. Absorbers and emitters. And you can think about it, it's the same as light, isn't it? Because it's visible light. Black as a color is an absence of light. So things look black when they absorb the light that falls on them. Things look white when they reflect the light that falls on them. So it's the same sort of rule that's at play there. You don't need to worry about, oh my goodness, what is better? Is blue better than green? That's not. It's always simple. It's either things are dark or they're light. They're the only things you need to worry about. So yeah, there we go. And so that's kind of like the different types of radiation. There's different types of way in which thermal energy can be moved about. So now let's think about how we put that into practice, because that can be simple, either recall, or statement of how convection currents are. They quite like that every now and again. But actually, what we can often think about is how do we use that to slow the process of heat transfer? and that is insulation. Okay, so insulation, it's another shun. We insulate materials, things, in order to slow the process of heating. Okay, that's the thing we do. We want the changes in temperature that occur to be as slow as possible. And so I've just got a few little examples. You don't need to recall definitive examples, but if you get presented with something, it's like, oh, okay, here's what's going on. And often it's just about what's happening here to minimize these three things. So let's talk about this first one. Mad people who decide to run really far and then they look annoyingly happy when they finished. And oh, look at them doing that smugness. So when people finish races, what you'll see often is actually you'll see people wearing these weird foil blankets, and you might also see them occasionally as emergency blankets and so on. And they're very thin, and you might sit there going like, why is this being used? What's the purpose of this foil blanket? Well, it's there to keep people warm. It's got a lot of advantages. It's very cheap to make, very light, so you can transport loads of them around without a lot of things. And you wouldn't be able to get a giant woolen blanket to people. And easy for people to hold on to. Now, why are they so essential? Well, if you've got someone who's sort of been doing a run, okay, let's say they're doing a half marathon run, they could be running for anywhere between 2 and 4 or 5 hours, okay. And when you run, you respire a lot, and you warm up. Okay, your core temperature increases. Your body responds by trying to make yourself emit more things, so you'll sweat more, but you also radiate more, because what will happen, as you can see from this lady here, the blood rushes to your face, you tend to go a bit red, and what will happen is that your body is basically dumping energy out into the atmosphere, okay, at a very high rate. And that's because as you're running, you're replacing that energy. So this energy is being dumped out in order to stop your core temperature rising and causing you a problem. It's why also, when you start running, if you're somebody who starts running for the first time and you sort of lightly jog, you'll see people wearing, several layers, and then you'll see other people who will happily run around in very cold temperatures in just shorts and a t-shirt, because if you're running fast enough, you're going to generate enough energy. Now, thing is, what happens though when you stop? When you stop, suddenly your body is going to stop producing all this excess thermal energy your body needs to get rid of. But it takes a little bit of time for the rest of your body to cotton on to the fact that this has happened, because you reach a kind of an equilibrium of, or attempting to try and get rid of things. So you stop, and suddenly you stop radiating quite so much. You stop. You've still got the radiation. But you stop producing the energy because your muscles are no longer working. You're not. So suddenly your body is dumping loads of energy out, but nothing is now replacing it, and it can be cold. And suddenly you'll feel very, very, very cold. So what do we need to do? We need to try and stop as much of this as possible as leaving. And so what we do, we cover you in a big foil blanket, okay, which is shiny. Okay. Now, why is that helpful? Other than the fact that I've just managed to. Well, there's a few things that will happen. Think about what will happen to the energy that you radiate. Well, silver is a poor absorber of radiation. It's a good reflector. So what will happen? That radiation will be sent back to you. Boom. It doesn't get away. So that's one way in which this happens. Another way in which energy can relate to you is if you're warm, you can set up a convection current. You set up a convection, your body warms the air around you and it goes zooming off. So what happens to this sort of pocket of warm air? Well, it can't go anywhere. It's trapped. So it's just going to swirl around. And you're going to set up a convection current, but it's nice and trapped within the foil blanket. It doesn't matter that the bottom of the foil blanket is open, because actually what's down here is very cold air. So that's the dense stuff. It's going to sit at the bottom. So what you're going to have at the top is a nice, warm, snug convection current that keeps the air around you warm. You're trapping also a layer of air. Air itself is a good insulator. So, you're not conducting it away. So you're trapping it through various different methods. It's quite clever, quite ingenious. What have you needed? You just needed a piece of silver foil. Now, if you take your silver foil and you decide to go and lie on the floor in it, that's going to be a problem because it's a good conductor. It'll take that energy away from you. But as long as you sort of wrap it around the upper part of your body, it works out quite well. The shininess, we have a reflection, so that's going to stop. We're going to stop things running. We're trapping the layer of air around us, so that's going to stop convection, or at least it's going to stop convecting all the way up here. Because if your energy goes up there, it's gone. So that's all good. Let's think about another option. Let's do cavity walls first. There's cavity wall insulation and things. So, right, okay. By the way, you don't need to worry about trying to note down all these things. So here's sort of a building work, and what happens in many houses, what you have is you have your outer layer, and you have your inside layer. Ooh, and high accent. So you've got, and historically there would just be a gap, an air gap in between the two, and these air gaps can be very big. So you would have one layer, and then another layer, and then a big sort of air gap. And so here's the inside of the house, here's the outside of the house. So what we have is it says where is the temperature? If it's a cold day, well, it's on the outside. It's on the inside, sorry. In nice warm inside, maybe you've got a nice sense of like, thermal energy on the inside, so, and on the outside it's cold. So you'll get naturally conduction through. Now what would happen in the gap? In the gap, we'll set up a convection current because the air here will get warmed. It will, it'll spread out. The air becomes less dense, so it goes up, and you set up a convection current, and then eventually it'll swing down and move. Now the thing is that what people discovered is that inside these two layers, if this is an empty layer, well, what happens is this convection current can be really quite efficient. It can actually be set up, and it can also operate across the whole house. I mean, this might be not just one floor, but like several floors, and you get this huge convection current pulling energy away from, maybe this is the room you're in, but above you is a second floor and a third floor, and this just takes that energy away, a bit like a chimney. So what they do is instead they fill it, and even in old houses you can actually get into the inside layers and you inject it with sort of like foams that expand. What we do is we trap it, and this stuff is basically like a big thick woolen jumper. What it is got is, let's do it in green. It's lots of sort of little lines of things, and what they do is it's sort of like it's a sort of a foam. It's a foam, and what it's like is we are going to trap pockets of air. So let's look at this little bit here. Okay, so I've got some air in this little pocket. Well, okay, so it gets warmer. Where can it go? It can go up to here, and then oh no, I'm trapped. So all I can do is set up a convection current in this little zone. So it's like bubble wrap on a very, very just massive scale. I can only set it up in this sort of thing. My air that gets warmed up here can't convect all the way up to here in one go. So it's got to be convection current, set up some conduction, convection current, conduction, convection, conduction, convection, and this becomes very, very, very slow. By trapping the air, we now have a slow, the air can't move, so it can't set up a giant, big convection current, which means that, it takes a long time for that to get across. Eventually it will, and then you get to here, and then suddenly you've now got conduction again. But by having this middle bit takes a lot of time. This is used a lot. Double glazing. In double glazing, they don't just have a nice sort of like thing. You can't sort of fill double glazing windows with a big sort of foam because you can't see out of them. But what will they do? Well, they'll have 2 layers of windows, and they will have a vacuum in the middle. So you can't very easily set up. You can't set up a convection current at all. You're just reliant on radiation. It's great, fantastic use. So that's sort of an example of it in the real world. And let's take the thermos flask, the humble thermos flask. This is how a thermos flask, if you cut away into it, you might notice that thermos flasks, they tend to be quite sizable things, but they don't hold anywhere near as much liquid as their size seems to indicate. And if you look inside them, you'll see they're shiny. And this is a great one because it has stuff to deal with everything. So, and also, we've got hot or cold liquid because it doesn't matter which way the thermal energy is going. If it's going from the hot outside to the ice cold drink, or if it's going from a hot cup of coffee out to the outside, the same principle is going to slow it down in both ways. So let's say it is hot on the inside. Let's say we've got let's say we've got ice. Let's say, you know, we've got, let's do it backwards. So here, load of ice is in here. We've got ice water. Okay, so it's nice and cold. Right, so that means we're going to get energy is going to try and go from the outside. It's going to try and go in order to stop, you know, things, in order to stop things sort of getting out. So what do we have? Well, the first thing we've got is look at the outside layer. The outside layer is going to be some kind of plastic. Occasionally, you might have a silver layer on the very outside. There'll be a layer of plastic somewhere. So what we'll have is we will have a, you know, we need a solid. We need to coat this thing in a solid somewhere. So what we'll have is we'll have a plastic case. Even if you cover it over again with another silver layer, there'll be a plastic case. Plastic, non-insulator, is an insulator. Things will take time to coat. So, but eventually our conduction will happen and we'll get through eventually via conduction and we'll reach this first layer. And we get, what is it? A silvered surface layer. And look here, vacuum. Here is a vacuum inside this. So this is silver, vacuum, silver. So we've got a vacuum, which means we can't convect across this gap. Can't do that. The only way we can get across this gap is through radiation. But we've got silver. Silver means it's a poor emitter and it's a poor absorber. So it takes a bit of extra time for light, for thermal, sort of infrared radiation to be emitted from this point. And when it does, it gets over here and oh look, it is reflected back. And you're just going to trap light radiation in here for ages as it bounces back and forth. Now eventually things will get. So inside this sort of weird vacuum, it's just lots of radiation bouncing back and forth. Every time it reflects, it gets a little bit gets absorbed. So you're slowly warming things up, but it takes an age. It takes ages for things to come through. And then we've got to this point here. We've got a silvered surface on the inside, so we've got a poor emitter of radiation out here into the actual thing. But we will eventually then, we will finally get a thing where we actually will conduct into the water. And we're going to start warming this up. Now that takes ages. You can keep things cold for several hours. It's very, very, very efficient thermoflasks are at doing what they need to do. And it's largely based on the layers of plastic and this silvered layer with a vacuum in the middle. It's a wonderfully simple piece of device. Same thing happens if you've got something that's hot on the inside. The only addition, if you've got something that's hot, is the lid, which stops warm air convecting straight out of the device. That's not a problem with things that are cold because you'll just have a layer of cold air which won't go out into the warm air. But yeah, that's how we have that. So this is what we have. So what we're going to do is we're going to see a few sort of exam questions based on insulation. On each one, just remember, take them through in turn. Ask yourself the question, what is the heat transfer, what are the features that I'm seeing? So where's the hot thing? Where's the cold thing? So what direction is the heating going? And then what barriers are in the way? Are there sort of, think about this, right? Are there gaps of air, which means you're going to stop conduction because it needs a solid? Or are you using plastics instead of metals? So what are you doing that's going to stop conduction? Secondly, are you trapping the air, which is how you're going to stop the convection occurring? And thirdly, are you using silver colors, which is how you're going to stop the radiation? And those are the three things to think about in any sort of device. And so there's a few examples, and I've done a video of solving that problem, so have a look at them, see how you get on.